Hi everybody. Today we'll be looking at three different limiting reagents example labs. The first one is going to be sodium bicarbonate and acetic acid. Now those are both aqueous compounds. In other words, they dissolve in water. The first one, sodium bicarbonate, here's Na, it actually has a plus charge, and CO3H, or HCO3 in your flashcards, has a negative one charge, plus one, minus one. It's a formula unit. Over here we have acetic acid. Now all acids start with H's, so in this case it's HC2H3O2. H has a plus charge, that's this one right here, and then C2H123O2. And so this has a negative charge. It's called acetate, it's an anion. Plus one, minus one, it's all good. When this reaction occurs, there's actually a couple of different sub-reactions that ensue, and the final products are going to be sodium acetate, Na with a plus charge, and acetate, C2H3O2 with a negative charge, water, H2O, also known as H-OH, and carbon dioxide gas. And here's the balanced reaction down here. It's a 1 to 1 to 1 to 1 to 1 mole-to-mole ratio. I put in the molar masses just to save us some time. The second reaction we'll look at is going to be copper plus silver nitrate. So I showed you this reaction before. You take pure copper, I'm going to take some copper turnings and add some silver nitrate, aqueous silver nitrate to it, and wait a little while. And when we go back to look again, we'll see that there's some blue copper to nitrate solution in here. And you can see that there's some silver that's being made right here. This is a single replacement reaction. So notice that this doesn't have lithium, but please stop calling me a careless zebra. This is a good way to remember the reactivity series up here. So we have copper fighting with silver, and copper is here, and silver would be down lower. Copper takes the place of silver, and so this reaction occurs with a 1 to 2 to 2 to 1 mole-to-mole ratio. And we're going to look at which reagent is the limiting reagent. The third reaction we'll take a look at is potassium iodide and lead 2 nitrate. Now, potassium iodide is aqueous, lead 2 nitrate is also aqueous, but when they react, we make potassium nitrate, which is aqueous, but here's the kicker, lead 2 iodide, which is a solid compound. And if you don't believe me, you can look at your solubility chart, your study sheet up here, and find that lead 2 iodide up here is an exception to the rule. Okay, there it is right there. It's an exception to the rule, so it's not aqueous, it's a solid. And the rule for double replacement reactions is if you make more solids and or liquids and or gases, then yes, the reaction does occur. So aqueous, 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 solid, yep, I would expect this reaction to occur. Now when you balance it, it's a 2 to 1 to 2 to 1 mole ratio. And remember, I keep on saying mole ratios because I'm trying to emphasize it's not a grams to grams to grams to grams or liters to liters or anything else. It's just moles to moles ratios. And so those are the three reactions we're going to take a look at in the lab. Hey, so we're going to take a look at this first reaction, which is sodium bicarbonate and acetic acid. Some water in here. And no reactions occurring. It's just dissolving. It'll clear up in just a moment. Yeah, it's already clear. Then we're going to take some vinegar, acetic acid, C2H3O2. It's about a 5% solution. So for every 100 grams or 100 milliliters of water, there's about 5 grams of actual acetic acid in this. When this reacts, we expect to see sodium acetate, water, and CO2 form. First, so this is the vinegar. Baking soda. And you can see the bubbles. Right? But the bubbles stop. Something ran out. Come on, bubbles, keep going. I don't know what ran out yet. I maybe have suspicions. Let me add some more baking soda, see if that makes the bubbles come back again. Bubbles. Let me add some more. Some more. Oops. And the bubbles stop. No matter how much more baking soda, sodium bicarbonate that I add, the reaction just doesn't go anywhere. So that means that I can add this. This is the excess reagent. The limiting reagent has to be the vinegar. So let me add some vinegar, some acetic acid, and see if it starts reacting again. There's the bubbles. pretty much stopped. Something ran out. Maybe both things ran out at the same time, I don't know. But let me add a little bit more vinegar and see if that resurrects the reaction. So no bubbles, basically. Add some more vinegar. Oh, there come the bubbles back again. So I must have run out of the vinegar, right? That's the limiting reagent. Alright, let me add the whole darn thing here. Okay, so pull them out of vinegar. And the reaction stopped. Let me add some more baking soda. And, oh, there goes the reaction. Okay, so now all of a sudden, I had to add more baking soda. Add a little bit more. Now I'm out of this too. And the reaction's going like crazy. And it stops, ran out of something. So, limiting reagent can be either baking soda or vinegar, depends on how much I add. And remember, we need to balance this reaction and then think how much of each, how many moles of each do we have relative to the 1-to-1 mole-to-mole ratio. Okay, the second reaction that we're going to do involves copper and some silver nitrate. So I'm going to take some copper here, just take that much. We have 0.39 grams. You can write it down if you want to. And I'll take some silver nitrate and I'll just kind of randomly choose. It's kind of expensive, but well, you guys are worth a lot. So first thing, get the silver nitrate to become an aqueous solution. So I'll put it in a test tube, like so. Alright, add some water. So nitrate, even though silver is a heavy metal, and silver really does not like to become soluble, because it's bonded to nitrate, it will dissolve pretty fast. Looks like it's all in there. So we have 0.88 grams of silver nitrate in this. We'll wait for that reaction to occur because it takes a little while for this one. So it's been a few minutes and you can see the sparkly silver that is clinging to the copper filings there. You can also see that the solution is blue in color, and that indicates that there's copper 2 ions that are floating around there. So that would be copper 2 nitrate, aqueous. Not much pure copper left anymore, copper with a 0 charge.
I've been stirring it up like this, and that copper is just getting thinner and thinner and going away. That's how much is left. And the solution is getting more and more blue, and at the bottom of the test tube you can see that's all silver.
While this reaction is occurring, not too much copper left. Let me do my stoichiometry, figure out my limiting reagent. Got my periodic table, my calculator, my pencil, I'm ready to go.
Alright, so I got the molar masses already. Copper is just 63.5, silver nitrate 170, and I put a dot behind it indicating there's 3 sig figs. So I just use the AgNO3, I don't use the 2 for molar mass. Silver is 108, so don't use the 2 again. Copper 2 nitrate is 63, about 96 times 2. It's 188 grams per mole.
Alright, so let me figure out how many moles of copper that I had. 0.39 grams of copper, and then we had 0.88 grams of silver nitrate. I need my calculator. Moles equals grams over molar mass. Alright, and I need to calculate moles. Cover up moles, grams divided by molar mass. 0.39 grams. 0.39 grams divided by 63.5. 63.5 grams per mole gives me 0.00614 moles of copper. Silver nitrate, use the same type of calculation.
Moles equals grams, 0.88 divided by molar mass, 170. If I did my math right, it's
0.00518 moles. So I just sort of randomly selected 0.00614 moles of copper, 0.00518 moles of silver. Alright, how do we figure out the limiting reagent? Well, it's kind of silly how I do this, but it works great. You can do it either way, but I usually cover up the second one, the moles, and I say 1 is to 2 as 0.00614 is to x. Alright? So 1 is to 2, I can write it out here, 1 is to 2 as 0.00614 is to x, and I pretend I don't know how many moles are there. So I do my multiplication, so cross multiply.
0.00614 times 2 equals, alright, so that is 0.001228.
X is equal to 0.01228. All right, cover up the moles. 1 is to 2 as 0.006 is to 0.0123. Come on, 0.0123, I say, I pretend like I'm betting or something. Come on, 0.0123, you gotta have 0.0123, do I have it? No, I don't have 0.0123. I only have 0.005. That's not even close enough, close to what I need. So this is the limiting reagent. Silver nitrate is the limiting reagent. And so from now on, I do all my calculations based on this. This is how much I use. So now I want to figure out how much silver should I make in this test tube. How much silver will there be there? All right, so I say 2 is to 2, that's the same amount, as 0.00518. So I'm going to get that many moles of silver. How much copper nitrate, the blue stuff in the solution, I'd have to dry that to get it out of there, but I can calculate it. And I'd say 2 moles is to 1 mole, because there's a 1 in front of this, as 0.00518 is to half of 0.00518 is 0.00209, I do believe. So that's how many moles of this. So now it's really easy to figure out how many grams of silver will I make, how many grams of copper 2 nitrate will I make by using this. Grams equals moles times molar mass. Multiply those two. Let me do it.
0.00518 times 108 equals?
I should make 0.559 grams of silver.
And then how many grams of copper 2 nitrate should I make? Moles times molar mass is 0.00209 times 180 equals?
I should make 0.393 grams of copper nitrate. Alright, so that's how you do limiting reagents. So now all I have to do is wait for this reaction to finish. Alright, and then I want to separate out the silver in here from the copper 2 nitrate, and I'll do that by filtration. Then I have to dry it and weigh it again after it's dry and see how much silver I end up with. I'm hoping for, I should get 0.559 grams of silver in the bottom of this test tube. Okay, we're one step away from the big finish. I'm going to try and filter out the silver and see how much I got. So I weigh my filter paper, 1.19 grams. Fold it up in half like a taco, half again, open it up so it's like an ice cream cone. Put it in my funnel. Alright, give it one last chance to react. There's still some copper left in there, which makes sense because according to our reaction, silver nitrate was the limiting reagent and copper was in excess. So there's some copper here that just stays and stays and stays. So I'm going to pour this whole mess into my filter paper right now. Get all the silver off of there. I think I did a good job. Hey, you know what I can do right now? I can dry this copper and see how much I have left. That's a pretty common question. How much copper did not react? So we know we have excess copper. How much excess is there? Still have some silver in there. I got to get that out.
So use a little bit more distilled water, shake it, pour it through. Do it again. Shake it, and pour the silver through. Maybe one more time if I can get it all. There's a little bit left in there. Shake it and pour. I think that's just about it. A little bit maybe. Alright, so
got the silver in here in the filter paper. The filter paper is all wet, so I've got to let the whole thing dry. I guess I'll dry it overnight. And then I'll come back and weigh it, and I should find that filter paper weighs 0.559 grams more than it did when the filter paper was empty, when there was nothing on it. This is the third example of limiting reagents and excess reagents, and so this is potassium iodide and lead 2 nitrate. I just got done weighing out some potassium iodide and lead 2 nitrate. So solids, add some water to them, then they become aqueous. You can see through it. Aqueous, you can also look it up on your periodic table. So potassium iodide, it's a K with a +1 and I with a -1. Loses an electron, gains an electron, opposites attract. That's a formula unit. And then lead 2 nitrate is here. I just weighed out 23.86 grams of lead 2 nitrate. Pb gets a +2 charge. We have to say Roman numeral 2 because lead is from the middle of the periodic table. Nitrate, I've got that memorized from my flashcards. It has a -1 charge. +2 -1, crisscross applesauce, PbNO3 1 Pb with a 2+ and a nitrate and a nitrate. Grand total, how many atoms? We've got 1 atom of lead, 1 nitrogen, 3 oxygens, plus another nitrogen, plus another 3 oxygens. So that's 3 plus 3 is 6, 7, 8, 9 atoms grand total in lead 2 nitrate. Well, if this reacts, we should have a double replacement reaction. The rule for double replacement reactions is if it will go if there's more solids and or liquids and or gases over here. And if they switch partners, we should end up with K with NO3 and PB with I. So this will be potassium nitrate, and this is lead 2 iodide. Let's see, aqueous, aqueous, aqueous solid, should it go? Yes, it should go. So let's see if the reaction does indeed occur. I'm not going to do it just yet. I'm going to set this thing up. 17.84 grams, 17.84 grams of Ki, 23.86 grams of lead 2 nitrate. How much of these reactants should we make, and which of these is the limiting reagent? That's what we base our calculations on. Which one? Moles, grams, molar mass. I want to calculate the moles, grams divided by molar mass.
So, grams is 17.84, follow along. Divided by 166, 166, so 3 there. We end up with
0.107 moles of potassium iodide, and
23.86 grams of lead 2 nitrate divided by 331 grams per mole. That's from the periodic table. Also, make sure you do not use the coefficient. That's the number in front. Don't use that when you calculate mole mass. Anyway, divide those, I get
0.0721 moles of lead 2 nitrate. All right, here's how you figure out sig figs. Remember, I said it's kind of sounds silly if you do it right. All right, you want to make like it's a big competition. You say 2 is to 1 as 0.107 is to something, and you cover this up. All right, so 2 is to 1, half as much as 0.107 is to 0.0535. All right, so you cover up the moles on the second one, and you go 2 is to 1 as 0.107 is to, and then calculate it and say 0.0535. Come on, 0.0535. Come on, 0.0535. Do I have it? Oh, I have more than 0.0535. I've got 0.07. Yes, I've got extra of this. This is the excess reagent. This is the limiting reagent. Right here. LR, limiting reagent. The stuff that runs out, that limits the reaction, stops the reaction when it runs out. There's going to be extra of this. So, how much should I get here? 2 is to 2, as 0.107 is to 0.107. 2 is to 1, there's a 1 in front of this one, as 0.107 is to 0.0535. So now let's calculate the number of grams of potassium nitrate and lead 2 iodide we should make. All right, so to calculate the grams, it's moles times molar mass, 0.107 times 101, 10.8 grams, 10.8 grams. And over here, 0.0535 times 461 grams per mole. Ooh, that's heavy. 24.7 grams. And so that's how much product we should make if the reaction goes. And so let's see. It's a soluble compound. This one is soluble. I do have a little bit of, I put in too much lead nitrate here. Well, okay. Will a reaction occur? Oh, is that ever cool? Is that ever cool? One of my favorite reactions. Isn't that pretty? The yellow. And so, yeah. So the yellow stuff, you can't see through it. It's a solid. It doesn't look like a solid right now, but if I set it down and come back tomorrow, it'll probably settle to the bottom, and then I can filter it out. I can filter it out right now even. Yeah, and so that's how you do limiting reagents.